All right, if you've got an exam on corrosion coming up, you have come to the right place. We're going to cut right through all the dense theory and focus on the core concepts you absolutely need to know. Let's get these ideas locked in so you can ace that test. So, here's our game plan. We'll start with the fundamentals, the basic principles. Then we'll dig into what makes corrosion tick and what factors make it worse. After that, we'll look at how engineers actually fight back against it. And finally, we'll tie it all together with some real-world examples that are perfect for exam questions. Let's get into it.
Okay, first things first. We've got to build a solid foundation. You can't really tackle the problem if you don't understand what's actually happening at a chemical level. So let's define our terms.
At its heart, corrosion is really just nature's way of recycling. You see, a refined metal is in an unstable, high-energy state. It wants to get back to its natural, stable form, like an ore. And it does this in two main ways. Getting the difference between these two is absolutely your first key takeaway.
So on one side, you've got what's called dry or chemical corrosion. Think of this as a direct attack, like metal oxidizing in a super hot furnace. But the real villain of our story, the one we're going to focus on, is wet or electrochemical corrosion. This is the one that needs a liquid, an electrolyte, to get going, and believe me, it's responsible for most of the engineering headaches out there.
Now that we've zeroed in on wet corrosion, let's explore its most common and honestly most interesting form, galvanic corrosion. We'll also break down the factors that can crank up the speed of this process from a slow rust to a catastrophic failure.
You can bet this will be on your exam. The concept is actually pretty simple. When you have two different metals touching in a liquid, you create a tiny unintentional battery. One of those metals, the less noble one, literally sacrifices itself. It corrodes away to protect the other. And we can actually predict which metal will be the hero and which will be the victim using something called the galvanic series.
So what decides how fast this little battery works? Well, two things are super important. First, how far apart the two metals are on that galvanic series chart. The bigger the difference, the faster the corrosion. No surprise there. But it's the second factor, the area effect, that is the real kicker. Honestly, this is where things can get incredibly dangerous incredibly fast.
And this is the ratio you have to remember. If you have a massive surface of a noble metal, the cathode, and you connect it to a tiny piece of an active metal, the anode, all of that corrosive energy gets focused on that one tiny spot. Imagine a huge stainless steel plate held on with one little steel bolt. That bolt is going to dissolve at a terrifying rate. You absolutely have to get this concept. It explains so many real-world failures.
And of course, it's not just about the metals. The environment they're in plays a huge role. Think of things like heat, salt in the water, or the pH level. They're all accelerators. They just speed up the whole chemical reaction, turning a bad situation into a total disaster. Okay, enough doom and gloom about the problem. How do we actually fix it? This next section is all about the tools and strategies that engineers use to fight back and win the war against corrosion. The number one strategy is something called cathodic protection. The goal here is to cleverly force the thing you want to save to become the cathode in that battery we talked about, which means it physically can't corrode. You can do this in two ways. First, the simple way, sacrificial anodes. You just bolt on a chunk of a more active metal like zinc or aluminum and let it get eaten away instead. Or, for the big stuff, you use impressed current. This is like a powered system that uses an external DC source to flood the structure with protective electrons. It's way more powerful and perfect for huge assets like pipelines.
Now, the other big strategy is a lot more straightforward. Just put a barrier between the metal and the environment. This is your passive protection. On one hand, you have organic coatings, like paint or polymers that just physically block stuff. But then you have inorganic coatings. Think of galvanized steel. You're coating steel with zinc. Not only does that zinc act as a barrier, but if you scratch it, the zinc then acts as a sacrificial anode. It's like a two-for-one deal, providing both passive and active protection.
And this right here? This is probably the most important principle in all of modern corrosion control. It's all about synergy. You never ever rely on just one thing. The gold standard is to start with a really high-quality coating as your main line of defense, and then you add a cathodic protection system as a backup, a fail-safe that stands guard over any tiny scratches or holes in that coating.
Okay, let's take all this theory and see how it plays out in the real world. How do engineers use these principles to protect absolutely critical, multi-billion-dollar infrastructure? Pipelines are just a perfect example. I mean, think about it. They're buried in wet soil, an electrolyte, and they have fluids, often corrosive ones, flowing through them, another electrolyte. They are literally being attacked by corrosion from both the outside in and the inside out 24/7.
So how do you protect them? You guessed it, synergy in action. Step 1 is a super tough external coating. That's your main shield. Step 2 is an impressed current cathodic protection system that acts like a constant bodyguard, protecting any chinks in the armor. And of course, step 3 is continuous monitoring to make sure the whole system is working perfectly.
Now, here's a fantastic, kind of counterintuitive point that makes for a great exam question. You'd think that a pipeline sitting in the open ocean would be in the worst possible spot, right? Well, yes and no. Saltwater is very corrosive, but it's also very uniform and predictable. The real nightmare is on shore, where the soil can change from clay to sand to rock every few feet. This creates all these tiny, different environments, leading to unpredictable corrosion hotspots that are incredibly difficult to manage.
And let's be clear, corrosion isn't just about giant steel structures. If you zoom all the way down to the microscopic copper traces on a circuit board, you've got the exact same enemy. It doesn't take much. Just a little bit of humidity in the air and some airborne dust can create a tiny film of electrolyte, and bam, that's all you need to kick off a corrosive reaction that can kill the device.
And what do you know? The control strategy here follows that same layered philosophy we've been talking about. It starts with intrinsic design, just choosing more robust, corrosion-resistant materials to begin with. Then you add extrinsic barriers, like these super-thin conformal coatings that completely seal the electronics from moisture. And finally, you have incredibly strict environmental control during manufacturing to keep any and all contaminants out in the first place.
So, to wrap this all up for your exam, let's boil it down. 3 things you need to remember. 1. Wet corrosion is an electrochemical process. It's just a tiny battery. 2. The galvanic series, and especially that area effect, tells you how bad it's going to be. And 3. The best defense is always a system, a synergistic combination of coatings and cathodic protection. If you can get those 3 points down cold, you are going to be in fantastic shape. Now go and crush that exam. Good luck.